In this video we will talk about pragmatism in physics-based modeling, PPBM, applied to the COGNITWIN CDNUR use case on ladle erosion. Here we see an image of a steel ladle, which is a ceramically lined cup or container that is designed for treatment and transport of liquid steel. Typical steel mass can be around 140 tons. The challenge here is to develop a model that can predict the erosion of the lining, such that we can know if it is safe to use the lining one more time. If a sudden leak happens, very hot steel will leak out of the ladle, and this can have disastrous consequences for the people around. The model should help also increasing the knowledge of the operators. To the left we see a cross-section of the ladle showing refractory bricks and outer steel casing. To the right we see a still hot ladle waiting to be cooled down and later have the wear lining demolished and after that relined for a new use. Here we see a principal sketch of a ladle with blue steel, red slug on the top and brown refractory. Bubbles are injected from the bottom. The gas bubbles result in strong flows in both steel and the slag. The slag is much lighter than the steel and floats on the top. Heat is supplied through the system through the heating electrodes that we see coming from above. Added heat is needed to melt and to heat up additions, but also to compensate for heat loss from the steel to the refractory and also to the external environment. This slide shows an overview over the pragmatism-based method. Here we see a number of boxes with numbers, and if we look into the upper part, we see the problem identification and context identification as a first part of the pragmatic modeling framework. This contains the industrial use case, analytical context, and definition of actors, roles, and responsibilities. So this is about problem and context identification to describe accurately the purpose of the model and the quantitative output data from the model, what that should be, and include the time constraints and other accuracy requirements. We can also see that there is a box 2, blue box there, analytical strategy and plan. This is about overall model design, resulting in a specification document. And if you go to the number 3, about architecture and analytical framework. In this part, we design both the experiments and decides details of the data structures and related analysis, including model and simulation entities. We have also a part 4 which follows after part 3, which is about execution workflows. Here we orchestrate the analysis, simulations, and experiments. Experiments in this context may be both physical experiments done as a part of the model development, or it can be numerical experiments, or actually data that we are going to request from the process. And here we orchestrate the workflow of experiments, the models and the simulations, and execute related data analysis. Model tuning to the data is a part of this step number 4. Step number 5 is the evaluation of the solution. Here we look into the outcome of the development, and here we have, in our case, a model that can deliver certain prediction results. In addition, we have a numerical code that can be applied as an element in multiple applications. such as cognitive digital twins or other applications for asset management and optimization. And the sixth point, which is not discussed more in detail right now, is about conclusions and communications. This we will come back to in a few slides. Here we look into a modified workflow that we applied for developing this model for the CDNOR use case. Here we can see on the top we have the industry case owners and industry's process team and industrial experts, and we have the solution architects. And what is special here is that this model was developed with a very slim team, with basically 2 solution architects and supported by one case owner from the industry. So first of all, we need to have the case definition with quantitative objectives that we have already seen above. What are the main points there? And when the definition is iterated between the solution architects and the industry case owner, we can go into an further detailing, doing clarifications of the case, look into the requirements and define the use case. And normally, as it was in our case, this is an iterative process. So we will work on the use case, look into what are the needs, and check if basically the involved physics is properly understood. If not, we have to involve the specialist from the industry, from the literature, or from other sources. Now we have also an other loop to the right about the data. So to work with the development like we have done, there is a lot of data from the industry. So we need to collect the data, which is going to be very valuable for model tuning and also for model validation. So we need to understand the data properly. And this is also a very time-consuming exercise, because there are, as we have found, many issues with the data that must be sorted out. So we have to communicate with the industry case owner, and also the case owner will have to involve the process team and industrial expert to answer these questions. When all these things are clarified, we can work on with the model specification. So we have clarified the requirements, we have the use case, we are developing a model specification. That will be a very detailed one, with all the physics and all the numerics that is needed to solve the problem. So next step will be to work on the coding of the model. When the model is coded, we can start with some model optimization, tuning. And then the question is, of course, can the model reproduce the data or not? So in this case, we have some data that we use for tuning, some data that we use for model validation. Normally it will be a first result that the model cannot reproduce the data. So we have to go back and see what is the issue. Are we missing physics? Are we missing data, or is there something wrong with the data? So basically from here we can activate both loops, both the left and the right loops, upper loops can be activated. And if the model can reproduce data, then we have a model that we can start to use. We have a direct prediction from the PPBM model. If we don't have a model that can predict, but we can improve the prediction capabilities by using some machine learning, AI type of methods. So this can add another level of hybridization into the model. We can do that, and thanks to this, we can also have a model with good prediction capabilities. Now, in our case, this loop is not developed to the extent that we wished, but the model is developed in such a way that it can be used for this and extended by this possibility. And basically we can say that we iterated all the loops many times, which can be seen from this diagram. So a little bit about the physics-based model development. The target was to predict the evolution of temperature and erosion pattern over the lifetime of a ladle. That means that a ladle is used multiple times, and we have to accumulate the data from time to time and simulate the behavior of the refractory and the temperature basically through the life of a ladle. And the model to be used as a physical-based digital twin, but also as an element of an hybrid twin, as we discussed, which is a hybrid with respect to AI or machine learning methods, and optimally as a cognitive digital twin. The model should read operational data, which was the case for us. We read a lot of online data, both static and transient data. And after deployment of the model, we should also read online data, which also has been investigated. However, in this sort of cases, the online data is not online immediately, but after some time. So we could call it semi-online. And in our case, we see that the predicted temperatures for the outer surface of the ladle could be used to assess internal erosion states and possibly steel intrusion into the permanent refractory. This point we will come back to briefly later. The phenomena the model is considering is thermal conduction in the materials, in between materials, convection by gas purging, waves on the surface, natural convection when there is no bubbling, the effect of the heater, what happens with the slag and the metal, the refractory, and we have thermal radiation, refractory dissolution into the liquid, steel and slag. We have also to deal with phase enthalpies of slag and metal to handle the phenomena of melting and dissolution. And composition and temperature dependent solubility of the refractory is also an important issue. What was not considered is the erosion due to thermal shocks during filling of the ladle, and also phenomena above the liquid level in the ladle. In this slide, we see the setup of bricks. To the right, we see a layer of steel, and we have different layers of lining. And the 3 bricks to the left are the wear lining, which is going to be eroded, and the model will handle the erosion and or thickness reduction of this layer. And this also corresponds to the numerical model. So the squares we see here corresponds to the numerical nodes in the model, and here the temperature for that brick, the average temperature, volume average temperature, is stored in these points. We see also that there is heat lost to the external by radiation and by different convection methods. And on the left hand side we have interaction with the slag and the steel, and there can be both convection, but if this is above the melt level, it can also be radiation that contributes to the heat transfer on the left side. This figure shows the simulation of flow driven by gas bubbles. So the gas bubbles are simulated using Lagrangian tracking methods, and most of the tracks now are seen as red lines moving up from the center here. This is a two-dimensional simulation, while in reality the system is three-dimensional. So we decided to make simplification here to make it possible to have a fast model. On the top there is red slag, which is being pushed to the side by the upcoming steel flow. And the arrows that we see indicate the flows in the steel. So we simulated a number of scenarios here with different gas flow rates and also different vacuum pressures above the melt. The vacuum pressure above the melt is important because in the case of low pressure, the gas bubbles expand dramatically in the upper part of the ladle, creating much stronger flows in the liquid. When everything was coded and ready to test and compare with the data, tuning became necessary. So, first of all, we had to do basic checks of the model to check consistency of the model. But we can also use the model to check external consistency. That means how does the model compare to data? We found that by using the model that the first temperature points that was measured could not be true. And after checking, it was found that that was not the case. So we can say that in cases like this, the model could reveal problems with the data because the model conserves mass, energy, and momentum. So that is a way to also check data consistency. And all the physical properties, as well as heat and mass transfer coefficient, and things like the efficiency of the electrode, these are tunable values. All details about the tuning can be found in the paper that's going to be referred to at the end. Here we see predicted temperatures in a slab of the ladle wall. And this is shown for the end of a heat. We also see the predicted erosion profiles. To the left we see that the large erosion close to the steel surface has led to some higher steel casing temperatures. This could be spotted by a thermal camera. To the right we see the temperature distribution through the wall. Now we see the predicted steel temperatures together with measured temperatures. The predictions is the blue curve and the measurements are the orange curve. The red curve shows electric energy added to the steel and the slag. Here we may note that the first measured temperature is not an measured temperature. That's something that was left over from the previous heat. The model had predicted how much is eroded at the end life of the lining. And the operator decided that the lining should be demolished at some stage. And this is what the model has predicted when the ladle lining was decided for demolition. We see the black line, which is the prediction from the two-dimensional model. We see the left and the right side of the ladle that has quite different erosion levels. We may note that the measured erosion is the maximum point on each half part of the ladle, not the average values. And the yellow line is the average of the two, which we can compare with the black line, which is the predicted erosion. We also see that there is something which is not so well predicted, here noted at the splash-based erosion. So this area is above the level of the slag and the metal. This is some special erosion phenomena that is not accounted for in the model. We have mentioned the concept of campaigns. Just to be sure that this is understood, a campaign here is what happens from a ladle is relined during its life until the lining is so much eroded that it has to be taken out for, again, relining. So the campaign is basically any series of events that can stretch over, say, from 70 to maybe 100 different heats before the ladle is so much eroded that it's dangerous to use. So this shows a plot of the fractional campaigns that have different numbers of heats. So of course we should want to see that there is a big consistent bar here with the high number of hits per campaign, but we see that there is quite some variation. And there are some campaigns that last for a very long time, but there are also some one which is lasting much fewer heats. So to the left we see that there is actually a few campaigns with a quite low, like 15% less heats than the average. The maximum is roughly 10% above the average. And it's been thought that to make a model, the campaigns with a few hits should be taken away because they are outliers. But we found that our model could predict equally well both the campaigns with low number of hits as for the high number of hits. So here we will look into the pragmatism achievements. The model was developed to be fast, and that was the case. The model can run 1 year of simulations in a few hours. And it can also be run in parallel if needed. Then you can probably run this model for 1 year in less than 1 hour. The model is also applying clear physical mechanism which can be used to improve the process understanding. So it's very important that when we have pure physical mechanism, we can play with those and we can see how this impacts the life of the ladle. The model is modularized, and that is an advantage because it can easily be customized to different tasks. In our case, there is written a number of scripts that can use this model in many different ways depending on the needs. And because the model of the modularized structure, we can also easily improve the model over time as more information, more understanding is available. The model is also designed such that it can easily be extended to full 2D. While we did not do full 2D but a quasi 2D approach. And we can do a full 3D extension. This is possible, but it is not recommended because this will take excessively long time and will not be able to fulfill the overall targets to have a fast model that can be running years of operation in a short time. Basically, with a 3D model, it is not possible to do any tuning which is relevant. It will be very difficult. Necessary modular tuning indicates that steel may penetrate in between the bricks. That is what we have seen. This can be deduced from the thermal model only and may explain preliminary thermal images which have shown hotter regions in the lower part of the ladle, where erosion level is not as high as in the upper part. So we have come to the conclusion that the model is a valuable consultant for operators and is serving as input to cognition approaches such as knowledge graphs. We will now like to conclude this work. So first of all, we have seen that the pragmatism in industrial modeling methodology was applied and extended to the development of a model for ladle refractory lifetime prediction. Major contributions of the methodology were that processes in the metallurgy industry are complex and has many dimensions. Operational data will have many challenges, and sometimes the data does not express what it seemingly is supposed to express. Therefore, it is critical that the solution architects have some experience with this type of industry in order to have good communications with the industry experts. Second point is that developing a model based on a slim team, like in our case, 2 scientists and 1 from the industry. This work should be stretched out in time, allowing multiple iterations in the development process. So allocating large funding resources to be consumed over a short time would be very costly and produce less valuable results. We also see that it will be an advantage that the funding to follow up the work could be extended for some time out over the original development project period. And for the third, a well-defined tuning strategy was defined. In this case, exact tuning was not possible as the data relevant for operation is monitored and not data that would be good for model tuning and validation. As a result, only approximate tuning is possible. Tuning should assure that all qualitative variations in the data is accommodated for. In this case, the model can be used in a semi-quantitative manner. Therefore, the combinations of model predictions, visual inspections of ladle refractory and operators' experience altogether make the foundation for the decision of the operator to decide that the lining should be demolished or not. And we also list the repository where the numerical model can be found on GitHub. So this model does not have, of course, the CDNOR's input data. It has just an example data set that can be used, and then the users must fill in with their own data. And there are 2 publications that is going to be available soon. One is on a pragmatical physics-based model for ladle lifetime prediction. This is about the numerics and the physics. It will be submitted to the JSIM special edition on computational modeling. And the other paper is about pragmatism industrial modeling applied to ladle lifetime in the steel industry. This is about the PPBM method and how this was applied in the development of this model.